So question 22. A group of engineers are testing a new car. They are investigating how the braking distance x of the car varies with its initial speed u when a constant braking force is applied. Figure 22 shows the data points plotted on a u squared against x graph. The straight line of best fit has been drawn through the data points. The theoretical relationship between u and x is u squared equals 2ax, where a is the magnitude of the deceleration of the car. Okay, so part A, figure 22 shows that the straight line does not pass through the origin because of a systematic error in the measurements of the braking distance x, and the u squared values are accurate. Suggest why a systematic error in x does not introduce any difference between the actual value of the experimental value for the deceleration of the car. Okay, so if we get myself a pen and have a look back, so if we look at our formula here, we've got u squared is equal to 2ax, we've got the u squared on the y-axis, and we've got x on the x-axis. So if we look at y equals mx plus c, because we've got a straight line, we can see that we've got u squared on there is equal to 2a multiplied by x, and in theory we haven't got in this here we haven't got an intercept, but the systematic error is bringing in the intercept, but it shouldn't matter because the acceleration is worked out from the gradient of the line, and that's not going to change, so we'll just put that in. So the gradient of the line remains unchanged. Oh, what happened there? So this has no effect on the calculation of the acceleration. Or deceleration. Okay, now let's move on to part B. It tells us that the mass of the car is 920 kilograms, and we've got to use the gradient of the line drawn in figure 22 to determine the braking force F acting on the car. So what we'll need to do is work out the gradient. Every time we use a graph, let's make sure we are looking at our units and seeing if we've got anything untoward, any powers of 10 or any prefixes. We haven't, so meters squared seconds to the minus 2 SI units, and meters down here. Now when it comes to drawing a gradient of the line, you will need to choose 2 points that are really far apart from each other. So I would say, oh, that's meant to be colouring in. Let's go for a different colour so it highlights a bit better. Let's try a red. So I would say we've got that point there, that's a nice point, and I'd be tempted to use that point there as another nice little point. So the coordinates of this point I would say is 50, and if we come dotted back down to here, we're coming through at this point, so we're between 600 and 800, so we've got 10 little squares, so each little square is representing 20, so I would say that this is 760. And we'll do the same for my little point down here, and I would say that that coordinate is 10, and again each one of these is 20, so 180, 160, 140 and 120. The gradient of the line, difference in y over the difference in x, so that's going to give me 760 take away 120 divided by 50 take away 10, so that is giving me 640 divided by 40, which is 16. Okay, so let's just go back here. I know the gradient is 16. So the gradient of the line, if we remember that we've got the equation u squared is equal to 2ax. So what I'm saying here, the gradient of the line is 2a. So 2a is equal to 16. Therefore the acceleration or the deceleration of the car is going to be 8 meters per second squared. And now we just use F equals ma and substitute in for the mass of the car, 920 kilograms, multiplied by my 8 meters per second squared. And that gives me an answer on my calculator of 7360. So going to probably two significant figures, I would say 7,400 newtons.